presented by Caltech.
So it's my great pleasure to introduce Maria Spiropulu, especially since I was on the faculty committee that proposed hiring Maria here in 2009. And I had Maria in my office yesterday, and I thought, so this is my first Watson lecture introduction. It would be nice to do something more than just read her resume. So I asked Maria, can you give me a funny story or something you'd like to say about yourself? And she said, well, I don't know. When we had the last high energy physics Watson lecture, it was Harvey Newman right after the discovery of the Higgs. And the introduction was given by Mark Wise, who's one of our theoretical physicists who's also very amusing. And he presented Harvey with a pair of boxer shorts and noted that Harvey had flown across the Atlantic 700 times back and forth to CERN. And I thought, Maria said, I don't want any boxer shorts, and I don't know how many times I've flown across the Atlantic. So I decided to just tell you a little bit about Maria's background, because I figured I can't trump Mark Wise. So Maria was born in West Macedonia, Greece, which I looked up on Wikipedia. It looks very beautiful and exotic. It's sort of the northwest part of Greece, where she was an undergraduate at Aristotle University. So then she downgraded to a much less exotic location for graduate school, to Harvard University in Cambridge, where she did her thesis at the Collider detector at Fermilab. And there's kind of a fun fact here that often physicists trace their academic lineage. So you have a thesis advisor, and your thesis advisor has a thesis advisor, et cetera. So Maria's great-grandfather is a very famous physicist named Enrico Fermi. So she can trace her lineage directly back to him. And so quite appropriately, she went to become the Enrico Fermi Fellow at the University of Chicago as a postdoc, and then continued at Fermi National Accelerator Lab, where she worked on the compact muon solenoid. She then moved to CERN as on the physics staff, and she got tenure. And amazingly, in 2009, we managed to convince her to give up that and come to Caltech. She says she did so because of the great excitement she had about working with Caltech undergraduates and graduate students, which she's done very successfully since. So her research interests are in discovery of physics beyond the Higgs. She'll trump Harvey Newman and tell you what we hope to find after the Higgs: dark matter, new detector technologies, and data analysis techniques. She's also very involved in science policy and advocating for science, technology, engineering, and medicine research funding in Washington. She's been widely recognized for her leadership in the field of particle physics. She was elected as a fellow of the American Academy of Arts and Sciences, which is a big deal, in 2010, for her leadership in experimental high-energy physics, in particular for her pioneering efforts in the experimental search for supersymmetry and extra dimensions. She was elected as a fellow of the American Physical Society in 2014, and what she's going to tell us about is one of the most important events in physics of the last decades, which is the discovery of the Higgs boson, but further, the implications of this discovery and new puzzles that are associated with it. So without further ado, Maria Spiropulu.
Thank you. Thank you, Fiona. Thank you, everybody, for being here. It's a pleasure to be here to talk to you today about the complex quantum cosmos. And I'm pretty sure that my students feel that they will be pretty happy to be great-great-great-grandchildren of Enrico Fermi. And some of them are applying for the Enrico Fermi Fellowship as we speak. So what I'm going to be talking about, we're going to go on a hopscotch travel in particle physics, which started, as it turns out, with cosmic rays, with discoveries of new particles in cosmic rays, here at Caltech, and also with collaborators from Europe. And I'm going to tie it in between the big and the microscopic, and see what's happening in between, where we have the discovery of the Higgs. So it's going to be a winding hopscotch kind of story that we are going to talk. Now, the takeaway message from gathering all the information from cosmology, astronomy, particle physics, theoretical considerations today and in the past century, it seems that our cosmos, and our cosmos is nature or the universe, is quantum and complex in the way it manifests in physics phenomena and also in its source. And I would argue that this includes empty space, so the vacuum, and probably, this is a bit getting out on a limb here, space-time itself. So we're going to go into different scales, with the small scale being on the one side, where we have particles and tracks, particles that move with the speed of light, and on the other side, the cosmos, the way we explore it with telescopes and space probes, and we try to figure out all the way to the edge of the universe how to characterize it. One of the crowning achievements in cosmology today is what we call the cosmic microwave background. What we see here is a detailed all-sky picture of the universe when it was infant. We have measured the age of the universe to be 13.7 billion years. And this is 13.7 billion years minus 380,000 years. So it's really at the very beginning of the universe that we see this type of temperature fluctuations. It's the first, almost the first light that we can see from the universe. The different colors here are describing indeed the fluctuations, and they correspond to seeds of what will become the scale, the structure of the universe, so the galaxies and the stars. So the colors that are red, these are the seeds of the really large-scale structure of the universe. Now, these have been measured in detail. The range here is plus minus 200 microkelvin, and we think that they match what we expect as small thermal variations that are generated by quantum fluctuations of matter when you put it in very, very tiny space. So the source of this, we think, has to do with quantum fluctuations indeed. And then they expand in order to make the universe as we see it today. This is from 9 years of the WMAP, which is the Wilkinson microwave anisotropy probe. But we are at Caltech, so we should say that before that, there was the boomerang experiment, which was a balloon observations of millimetric extragalactic reaction and geophysics, which was an experiment that was led by a Caltech previous PMA chair, Andrew Lang, and this was in Nature in 2000 when they published their results with the cosmic microwave background anisotropies. In fact, it was before the WMAP. So if we go and look a little bit at the timeline of the universe, or the history of the universe, what we have here spanning from 10 to the minus 32 seconds after some singularity here that people call the Big Bang, where we think the source of the quantum fluctuations are. So from this point on, 10 to the minus 32 seconds, all the way to 13.7, 13.8 billion years, which is now, where we have what we call the modern universe. And the modern universe is what we see in the sky and what we observe. In this period of time, the first cosmic event that we have measured in physics is actually the Higgs. The Higgs is what we call electroweak symmetry breaking, is the time when the Higgs field turns on by itself and particles acquire the masses. You have heard about the Higgs in the past 3 years quite a lot. It's the mass giver to the particles of all the particles of the Standard Model, and this is the time when the Higgs field turns on. So the temperature that corresponds to that is very high, and the energy that corresponds to that is something that we call the TeV scale. So here we have a bunch of scales in this evolution of the universe. And in fact, actually I wanted to say that two of my colleagues, Jamie Bock and Sunil Golwala, are continuing the search in this area in cosmology very successfully with other missions and following also on Andrew Lang's steps. And one of the questions that we have about the universe, having seen how big it is the question, why the universe is so big? In particle physics, we call these questions, we call this type of question the hierarchy of the scales. Why do we need to have such extreme scales in nature? Here we have the scale, which is the Hubble scale, which is how big the universe is. We have the Planck scale, which is where the source we think of these quantum fluctuations are. It is it is a number, but we think that there is physics here. And then we have intermediate scales where we see phenomena that are pretty interesting. We have the Standard Model and the LHC here in those intermediate scales. We have life in between, chemistry in between, we have biology in between, and then we have neutrinos, which, as it turns out, the scale of the neutrinos, whether you call it energy scale or whether you call it the length scale, this type of scale is also the scale of the dark energy. And dark energy comes from these measurements that we were talking about, the cosmic microwave background, is the kind of expulsive force that propels the universe to expand in an accelerating way, as we measure it today. And we have measured it not only with the cosmic microwave background, we have measured it with supernova. Astronomers and cosmologists are doing this, and we know that this is how the universe evolves. The universe is accelerating. Now, the force, or the kind of mysterious energy that fills every cubic centimeter of space at the edge of space as space expands, is what we think is the dark energy. It's very mysterious, and it is the biggest component of the universe today. It wasn't always like that. So here I'm going to show you 3 simulations that show if this was, for example, the type of anisotropies that we had from the cosmic microwave background. And then I put in the simulation some dark matter, some dust, and some hydrogen. What is going to happen if I put all the laws of nature, and what I'm going to get? This was from 2010. It's the Virgo Consortium, which is a consortium of physicists with computer scientists that are using powerful supercomputers. And this is what we are getting when we look at that. So as the universe evolves in time from these fluctuations that we had initially, when we put the ingredients in, we are getting this large-scale structure. And here, in every node that we have, every light that we have, we're going to see it on the next one, we have galaxies and stars. And if we look at it at this particular length, I think this one was 150 megaparsec, this is how the universe looks like. Empty space, structure. And what is this structure? we're going to look on the next simulation here. And we're going to start seeing the same thing. This is one of a little speck here. The particles that they are putting in is billions of particles. Incidentally, this was using about 12,000 cores and produced terabytes of data. At the LHC, we're going to see a petabyte per second. I want you to remember that. But this is how the universe, this is how these simulations evolve. You take the virtual box of a few billion cubic light years. You put some billions of primordial particles, including dark matter. We're going to talk about dark matter a lot. You put the physics, you put all the physics rules, and then you let it go. And you get galaxies in every yellow dot, and you get this normal matter. And this purple underlying normal matter is dark matter. Now, it's going to go back, but so it's going still in at 3.9 megaparsecs. This is megaparsecs per Hubble constant. The Hubble constant and the constant of acceleration of the universe, it's about 70 kilometers per second for a galaxy that it is 1 megaparsec away. And we go backwards and we see again the fluctuations. So I'm going to show you the same simulation again, where this time it's even more powerful. There's more particles, and this is from an organization for a consortium called the Illustris project. Again, a computational simulation. They compare also with the data, and what we're going to see is on the left. The dark matter. This is the cube. Every slice of the cube is going to be the evolution, slice per slice, in the evolution of the universe. And then we're going to see structure of the universe occurring. This is the dark matter. This is the normal matter, gas, temperature. And here, in every node that it is light, is where the galaxies are. And so you see, this is how complex the universe is if you look at the large scales. And you have all these filaments, including on this dark matter, which is gravitational. We're going to come to this in a little more detail. But this is matter, this is dark matter. So dark matter hangs on where matter is, or matter hangs on where dark matter is. And I want to, okay, I have Fiona's picture here because I want to remind myself to tell you that not only we have dark matter and matter, we talked about the dark energy that it is making it expand, but we also have in every galaxy here, we've got black holes. On every galaxy, we've got black holes. So in the ingredients we are seeing in these simulations, and Fiona, as you know, she had sent a mission, a space mission, to actually explore and understand the physics of black holes. But you see the composition of what we saw in the large scale structure is normal matter, which includes gas and all the baryonic matter we're going to see, and then we've got also black holes. Now, this is the same picture again. Here we are with the Higgs. We talked about this mysterious force or pressure or the dark energy, the energy of every cubic centimeter of space that we have, which is of the order of 0.6, 0.7 eV, which we said in previously coincides with the scale of the mass of the neutrinos, which is a coincidence, but there it is. Or maybe it's not a coincidence. We have to explore this. Here is the Higgs, and one of the things that we are puzzled about is the empty space. So what is the empty space? From the cosmology point of view, we said that we measure the empty space, every cubic centimeter of the empty space, to have a finite energy, not zero. Empty is not zero. From the particle physics point of view, and possibly we have to explain this from the particle physics point of view, we have the vacuum. And the vacuum is looking like that, where if I actually put the movie on, it doesn't look like it's resting at all. This is the quantum vacuum, and there is particles and antiparticles being created. So the vacuum is not a vacuum. It's not an empty space at all. It's jiggly. It's very irritable. If you put particles on top of the vacuum, this is going to change, but this is the quantum vacuum. The question we have that has to do also with the Higgs is whether the Higgs vacuum, which is the electroweak vacuum, has to do anything with the dark energy, namely of the energy that is making the universe expand outwards with an acceleration. And the answer to this is if we sit down and do the equations, and I think in some of these links that I show you up there, you can find the calculation yourself, is we get an answer from particle physics, from quantum field theory, the standard model, we get an answer that it is 10 to the 120 wrong, off. We don't get the thing that we measure from the cosmic microwave background and from other sources of how we measure the dark energy. This is very puzzling. Now, in our story, we are going to see that for this Higgs, for this electroweak symmetry breaking, for the mass of the field, which is called the Higgs particle, we actually need a story that is bigger than the Higgs, because, again, of quantum corrections of this type to the mass of the Higgs. So this story is telling me that if I find the Higgs, and this is the kind of lecture I was giving 10 years ago, I was giving a lecture that I was very convinced that I will find supersymmetry, we will find supersymmetry, and within supersymmetry we will find the Higgs. Now we found the Higgs, and we don't have anything to protect it against quantum corrections, so something is very puzzling about that, and we're going to return to that. But one of the bonus of trying to put together the cosmology model with the particle physics model of the universe is to understand this part. So here is the budget, the budget of the energy density of the universe. We got 4% of free hydrogen. This 1% is this normal stuff, of which is 0.5% is stars, 0.3% large percent is neutrinos, and these are whimsical particles with very, very low mass. We're going to explore them when we talk about the standard model. Then we have a little bit of heavy elements, and then we have all of this pi here, all the blue, which is unknown stuff. We call it the dark matter, and we call it the dark energy. Most of the universe energy density budget is mysterious. It makes depending on how you see this, it makes you feel very special for this little piece that makes everything we know, which is probably the most useful of everything. So now I'm going to do a little detour on the 20th century physics revolutions, because we need to remember, we need to go through the foundations, and I find it useful when I talk about where this is all taking us with the Higgs and where we're going. I need it kind of useful to go and explore a few of the notions of relativity, so special and general relativity and quantum theory, and behind all three of them is Einstein, although he didn't like quantum theory too much. However, he got his Nobel Prize because of that. So, and I will explain a little bit about why he didn't like it, because it's not very likable, to be honest. So special theory of relativity is the theory, well, it's the theory of fast-moving objects. And a way to see this is the following. If I have two clocks here, and this is light bouncing on two mirrors, every time the light bounces, the clock turns. The clocks were turning the same. Now this clock, with these mirrors and this clock, are going fast with the speed of light, close to the speed of light. So now this one is ticking slower than this one, because the light has to do a bigger path. This is where everything was demolished about the nature, about the nature of space-time as Newton had it, that space and time are very rigid and permeating everything, and they are the stage for everything. Not at all. In the case of special theory of relativity, time dilates and the lengths contract. Why? Because we have to keep the speed of light at the speed of light constant, and everything else will change, but the speed of light will not. So you will change your space and the way you measure space and time, but not the way the velocity of light. Now, for those of you who went to see Interstellar, you have seen this. And this is where they arrive at Miller's planet, I think. Kip should correct me here if I'm wrong. Where this is very close to a black hole. And so they have gravitational dilation. It's very similar.
Go, 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 go. 7 years per hour here. Let's make it count.
Okay, so it's 7 years in Earth, 1 hour in Miller's planet. So every minute there, they have to do it. They have to make it count. And I have gotten many friends of mine who are teaching physics. They have gotten Kip's book, the Physics of Interstellar, and they are teaching kids black holes and relativity and so on using that book. So this is quite nice. So now we're going to move to another consideration that has to do with the general theory of relativity, which is also, in a sense, it's changing the notions of space-time. Now space-time is a fabric. It's like a geometrical construct. You put a mass, and the mass is changing the fabric of space and time, and then objects go around in this type of orbit, because exactly of the curved space-time, including also light rays. And this is why, and this is how the discovery of planets happened that were not predicted, even that they were there. So now, a parenthesis, this was the kind of space-time that we had before that, before the beginning of the 20th century. The space was a rigid stage. And time was a mathematical, eternal thing, and all the actions, all the physics phenomena were happening in this stage. The last part of the evolution of the 20th century is the quantum. And this is where things are going to become tricky. First of all, quantum mechanics would not have happened if we didn't have experimental indications. So experiment was the thing that was that pushed us to arrive to quantum mechanics. So if you hit here a tube, a glass tube with a gas, and you put a prism, you get these lines. These are pencil-sharp lines of different kind of wavelength. Where are these coming from? Why would these be here? This was a very puzzling phenomenon, that you would have these very pencil-sharp stripes of different color of light, different wavelengths. And what happened is this Bohr thought that, in fact, the atom was like a planetary system, and you had the electrons, but the electrons were disappearing from one orbit into another orbit and were giving off, which were discrete orbits, and were giving off particular wavelengths, particular energy of radiation, of light. So quantum mechanics, and that's the old quantum mechanics Niels Bohr model, which was explaining this type of lines. And by the way, this is how we see from the hydrogen from the stars, when we are measuring the stars and everything in the cosmos, we are seeing this type of lines, and we're measuring these. So quantum mechanics is our tool in order to measure the world. So now, when the electron moved from one orbit to another, it didn't actually traverse the space in between. It just disappeared from one and it appeared in the other. That was peculiar in the way of the formulation. And then, so there was nowhere electron in between, hence the stripes. Now, things are getting even hairier when we are going to talk about the double slit experiment, which you have heard many, many times and read about it, but I'm going to go through it quickly. Imagine that you have particles that you throw in between two slits. And if you are having particles, if you're having tennis balls or whatever, classically, you would see it going behind the slits, but not in the middle when there is a barrier. If you're doing this in quantum mechanics, as it turns out, you have the two slits, you do the experiment, and you see a percentage of hits exactly behind the wall and another percentage next to it in stripes. If the particles were really particles, that was really bizarre. So Schrödinger started thinking that maybe they're not particles, but the electrons, for example, if you're shooting electrons, maybe they're waves. And they knew about waves of water and waves of sound. So you calculate the waves, and you write an equation. This is Erwin Schrödinger. And you say, OK, these are waves. The electron is an extended, mushy object. A little bit of the electron is here. A little bit of the electron is there. That didn't make much sense. And Max Born corrected. He said it's not the wave of the electron, that the electron is a little bit here and a little bit there. It's a wave of probability. So it means that there is a probability. The wave of probability means that there is a probability to find the electron at this particular point. So the question that you are asking is not where is the electron, but what is the probability to find the electron at this particular space. So when you are at the trough, the probability is higher. When you are down, the probability is lower. Here, the probability is higher. Here, the probability is lower. And you find 33% of the hits are here, and the 7% are there. And therefore, we are living in a probabilistic interpretation of the particles or the waves. There are neither particles nor waves. There is a probability wave. And of course, we understand a little bit about probabilities from going and playing in the casino in Las Vegas, for example. So in 1927, this was a meeting, a monumental meeting of all these gentlemen, 28 of them, and one woman, 3% of women back then. We have improved at Caltech by a lot. So you can recognize many of them. Schrödinger is here. Holly Compton is here. Einstein is here. Marie Curie is here. We've got Balmer. We've got Dirac here. We've got all the names that basically in those few years, they clarified faster than any other time the most bizarre of notions in quantum mechanics. This was a meeting in Brussels, in the Metropole Hotel, and it was called Solvey after an industrialist who organized the meeting. And out of this meeting, this was the destruction of the classical concepts of physics, of space-time, specifically of space-time, and the introduction of quantum mechanics. So now everything that we have today in terms of electronics, transistors, lasers, integrated circuits, everything of everyday life is based essentially on quantum mechanics. If quantum mechanics went on strike today, we would be back in the Dark Ages or in the 19th century otherwise. So now beyond that, based on quantum mechanics, we have an increased understanding of new materials, and this one is one of the latest ones, graphene, which is a hexagonal carbon structure that has so much, that is so strong and it's so light. Recently in the news, one of our colleagues at the PMA, Nei Chang-ye, she has done a very big progress on this material. But we start using all these type of materials, nano carbon tubes, different quantum dots, and we start in our experiments at CERN and high energy physics, we start using them. So it's important to understand that it doesn't stop. Now, one thing about quantum mechanics that that is becoming even weirder. And the weird thing about the probabilistic of the quantum mechanics was that in discussions, for example, of the interpretations, there were many philosophical discussions. The discussion is, if I look at it, it's a particle. If I don't look at it, it's a wave. And so Einstein was saying, I want to know that the moon is there, whether I look at it or not. And he also said, for the probabilistic thing, he said, well, God doesn't throw dice. And this is where Bohr was telling him, stop telling God what to do. So there were all these discussions about interpreting quantum mechanics. But one of the most bizarre, literally bizarre things about quantum mechanics is what is called quantum entanglement. And quantum entanglement, for the longest of the times, is considered indeed a philosophical thing, because it tells us that when you have atomic systems that interact, they necessarily are entangled or necessarily are correlated in a way that the correlation never goes away. That means that if you have, that means also, or never going away, means that if I take them very far apart, they remember their interaction, they remember the way they interact. This is a little bit weird, because that says that we give up locality anymore. We don't have the physics at the local space, but it's a non-local thing. You take the particles far away, they remember what their interaction was with the initial particle. This is a positronium, which is a, well, I mean, this is, yes, an electron and a positron. These have some spin, and they have some quantum properties. When they are close together, they are having their spins up and down in a singlet state, so that up and down cancel out and make zero. The observer is here, and by the way, the system now is this, the locality, the non-locality of the system is that we have a system, and it doesn't matter where you take these two parts. All of these three are part of the same system, and there's no problem that if you take these far apart, that that the measurement you are going to make on one will reveal you what the other is instantaneously. So there's no what Einstein was calling this unacceptable, because of course, if you measure this one, this says, tell me if you are up or down, I have to be the opposite. And the other particle is telling him, I don't know until somebody measures me. Once you measure me, and this is according to Bohr, if you measure this guy to be up, then this guy will be down. Which is very puzzling according to Einstein, because he would say there has to be an interaction here. No information can move with faster than the speed of light. It cannot be instantaneous. So he was calling this spooky action at a distance. And he thought that it was really something about the quantum mechanics that is incomplete in terms of these notions. So in this sense, in this cartoon here, it says, don't go far away. Your signal cannot exceed the speed of light. This is what Einstein said. And he says, don't you worry. We are both part of the same system. Once you are married once, it doesn't matter if you got the divorce, forever. You are entangled forever. And this is, we took them half the universe, and this is a large system. So this is essentially giving up locality in that sense. We will come back to this notion, because this notion of entanglement is as puzzling as it is. It may have something to do with the complexity of space. So now we're going to go for the roundabout, which is a magnificent journey in particles, and we're going to talk about the standard theory of particles and forces. This is a quantum field theory. It's talking about the particles and their interactions, all the elementary particles and their interactions that we know, the forces of nature. It starts here, particle physics starts with cosmic rays in 1933. There he is Anderson here at Caltech. He got the Nobel Prize both for the discovery of the positron and the muon. The muon is here, and below is there. And these particles came from cosmic rays. There was a period of time here where accelerators started showing up, very tiny accelerators. The first cyclotron accelerator was made of brass and glue and wire. It costed $25. And it was 4 inches. You could have it in your palm. We're going to see a picture of it. Right now, the LHC, together with its experiment, costed $10 billion. So you see where we went. I mean, this is an exponential progress in terms of understanding also. Not only in terms of the cost, it's less than linear, in fact, if you make some metric. So the next big meeting that happened, like the meeting of Solvey, was a meeting in France where Louis Le Prince-Rinquet exclaimed that, gentlemen, we are invaded. Accelerators are taking over. Particle physics is not going to be anymore cosmic ray physics. It's going to be driven by accelerators. And in fact, indeed, we started building from this small $25 brass wire and glue construction where you apply electric field and you put particles in and then you throw them in a fixed target. We went into the magnificent Tevatron where we were colliding matter with antimatter, and beyond that we went to the LHC, of course, which is the highest energy collider of a Hadron Collider, with the future prospects of having even higher energy. So let's talk a little bit about the standard model. The standard model, foundations of the standard model is quantum mechanics, but it's not just quantum mechanics, the quantum mechanics of individual particles. It's quantum mechanics in the form of quantum field theory. You have a field that permeates space and time. It's a continuum function of space and time. You can consider it physical or mathematical. And then when you do quantum mechanics in this field, the thing that is happening is that you can have many particles, and the particles can decay. So it's not just you're doing quantum mechanics with 1 or 2 particles. It's a many-body system. It has infinite degrees of freedom. So it can describe, field theory can describe many-body particle system, and this is why it's used in high energy particle physics, and it actually describes all the interactions of all the particles with each other and all the forces. And the forces are mediators. So in terms of, for example, electromagnetism, instead of having a force between an electron and a positron, you have a mediator in between. You have a boson. This is a photon. So one of the founders of the quantum field theory, and actually who understood how to treat mathematically and take limits of the theory, so that when you have a theory that you can get infinite degrees of freedom, you will get infinities. So he figured out many clever ways, not only to describe the interactions with these wiggles and lines in a very different way than actually writing out many pages of very complicated equations or matrices, but he figured out also how to remove the infinities and get sensible results, together with Tomonaga and Dyson. So on the right side is again a simulation. This is on the lattice. This is a simplified, let's say, simulation of a 5-4, what we call a 5-4 field. Now, in order to do really simulations of this type of quantum fields, one would want a quantum computer. Maybe for the black hole also, where we think that there is it's a quantum construct that is very difficult to describe, we will need a quantum computer. So this is a simplified such simulation. So if we go to the standard model now, this is the way to describe it. U1 cross S, U2 cross S, U3. This is an equation that mathematicians will understand very well, very symmetric, very beautiful. The complexity of the standard model comes when you break the symmetry. When you break this symmetry, these are mathematical symbols. You break this symmetry, the electroweak symmetry, with the Higgs mechanism, you give masses to the particles. And that part here is all about the quarks and their interactions and their carriers, which are the gluons. So if I look at the standard model, this is the particles of the standard model, the quarks, the leptons, and the force carriers. And this is if I write it down completely with the phi being the Higgs, it will become like that. If I break the symmetry, I will have many, many more lines. So, and these kind of equations, they were developed not in one day or in 1 year, but in decades, that describe all the interactions of all these particles. This Mexican hat thing is the potential of the Higgs. This shows you the potential of the Higgs. And we're going to discuss a little bit what it means, what the symmetry breaking means when you have this type of potential. Instead of having the most symmetric solution that would be a particle sitting here, in fact, what will happen in nature is the particle will roll. So once the rolling happens, this is how the particles are getting mass. Now, we saw it in a very streamlined way there with that table where they have their quantum properties. If we look at their masses here, the quarks and the leptons, they have very, very different masses. They change by many orders of magnitudes. If you take the mass of the neutrino, which is tiny, to the mass of the top, there's many orders of magnitude. We don't know why. This is part of the questions we're asking in particle physics. And similarly, we categorize them as fermions with spin 1/2 and as bosons with spin 1. So I will make a pause here to say that supersymmetry that we didn't find is a symmetry that wants to have for every boson a partner that it is a fermion. For every spin 1, it wants a spin 1/2. Our structure of the standard model has those particles with 1/2, has those particles with spin 1, but the rest of the quantum properties are not such that you say, voila, here is supersymmetry. It isn't. We have to invent partners which are not just those among themselves, but superpartners and extend the symmetry, and this is the symmetry that we haven't found yet. Before I go on to supersymmetry, I will describe very fast another puzzle that we have, which we are struggling with in the standard model, which is the matter-antimatter asymmetry. So there is 1 in 10 billion asymmetry, we think, at the very beginning, at the singularity, where we had the so-called Big Bang. We think that we have 1 in 10 billion asymmetry between matter and antimatter, and this is why our universe is matter-dominated. There is a way that if those quarks that we saw in the tables, they are mixing with each other. Each of the quark has a name or a flavor and their quantum properties. If they mix with each other and they oscillate, which they do, there is a way that you can produce a phenomenon that explains this matter-antimatter asymmetry. Sadly, it's not enough. The observations that we have for how quarks mix, and they got Nobel Prizes for that as well. This is the mathematical way of how we say one goes to the other. So the up goes to the down, it goes to the strange, it goes to the bottom, and then the charm goes to the down, it goes to the strange, it goes to the bottom. If we calculate the couplings of these reactions, we're getting this mixing matrix, and it tells us how those flavors mix. You measure all these parameters, you measure some angles and some phases, and you find out, no, this is not enough. This is a 50 years program, and it's not enough to explain the matter-antimatter asymmetry. Incidentally, one of our high-energy physics colleagues, Professor Hitlin, he got now the Panofsky Prize. He was the spokesperson of the experiment Babar at SLAC, where they made some of these crucial measurements in order to understand matter-antimatter asymmetry. Nonetheless, we have another sector of the standard model particles, which are the neutrinos. Maybe they mix as well, and maybe they're mixing. The mixing is a quantum phenomenon. The mixing of these particles is a quantum phenomenon. Maybe this mixing is producing enough type of this violation, what we call charge parity violation, that can explain the matter-antimatter asymmetry. So far, we have not measured everything of that, but we know that we have an extended program in order to do that. And since this was the Nobel Prize of this year, I just want to say a few things, because also it's a very good example of quantum mechanics. We arrive at the sun where we have nuclear reactions. Neutrinos of the flavor of electron are produced here. 8 minutes later, they arrive on Earth, and guess what? They are not anymore only the neutrinos of the flavor electron. They are neutrinos of a different flavor, the flavor muon and the flavor tau, different kinds of neutrinos. What happened? You started with one and you arrived at the next one. So definite flavors, and now I change the color scheme like every person in physics in the middle of the book, you change notation. This is a flavor, is a definite flavor. This is the neutrino electron. This is the neutrino muon. This is the neutrino tau. And now the colors, I make them say this is nu1, nu2, nu3. And I'm saying that each one of these is the quantum mixture of those three. So a definite flavor does not have a definite mass, and those that are definite mass do not have a definite flavor. If I consider them, however, as I said, with my probabilistic way as waves, I can make them interfere, and I can make out of the three of these definite masses, I can make one definite flavor, and they oscillate, and they go from one flavor here into three flavors there. This is the Nobel Prize of 2015. One of our younger colleagues, Professor Patterson, he is preparing the program where we're sending intense neutrino beams all the way to Deadwood, as it turns out, in South Dakota, in order to make experiments at Homestake Mine to study these oscillations. Now, the neutrinos, as you saw in the energy budget of the universe, they are created about 1 second after the Big Bang, and we have today about 150 per cubic centimeter. So we have a lot of these particles compared to any other particles. And 100 billion of them per second are passing through our thumbnails. Now, you had a full Watson lecture, which I urge you to watch, by my colleague Harvey Newman on the LHC and the Higgs. We saw particles with spin 1/2. There were the fermions. We saw particles in the Standard Model with spin 1. There were the bosons. The bosons were the carriers of the forces. The electroweak force, which is electromagnetic and nuclear weak. The strong force for the gluons. We saw all these bosons there, that there were particles with spin 1. There was no elementary particle with spin 0 until we found the Higgs, which is truly a new fundamental force of nature, and is the first kind of a new particle that we found since the electron and the photon. One had 0, one had 1 spin, one had a 1/2 spin. Now the Higgs has 0 spin. It took a long time, huge international collaborations, a lot of money, and a lot of will to create the LHC. It's the most complex and highest in scale and in size, most complicated experiment that we have ever produced. Now, one thing about the LHC and the Higgs that it is very often, that I hear very often when I'm traveling to Washington and also at CERN, is that we would not, absolutely would not be able to do anything, to do anything with this data if we didn't really have computational, networking, transferring of the data. And the actual king of the transfers of the data is Professor Newman, my colleague, who we are working together at CMS. And not only the data that we get, I showed you simulations, the cosmic simulations with the terabytes of data in the many cores. Here at the LHC, we are exposed to 1 petabyte per second, and we are saving about 25 petabytes per year. This is a graph that I got from Fermilab, and it shows you, compared to all sorts of useful and unuseful data, even tweets, it shows you how the LHC has the biggest big data. And Harvey Newman has designed, since the very beginning, 15 years ago, a computing model on how exactly we're going to transfer the data, where the data goes, so that we don't actually break the web. If we put all the LHC data in the internet, we would have broken the internet. Let's see a small movie of where is the Large Hadron Collider. The Large Hadron Collider is in between Switzerland and France. It straddles the border. It's underneath 100 meters with a little bit of an inclination, so we don't send radioactivity to the airport. It's about 1 degree. This is one of the experiments. It's the competitive experiment. It's ATLAS. This is a 3-year time lapse of how they built one of their complex detectors, which is called electromagnetic calorimeter. This is the calorimeter that catches photons and electrons, particles that have the electromagnetic force. And this is how the tunnel looks like. These are superconducting magnets, which are 14 tons each. And they are composed of superconductor niobium titanium superconductor threaded that is about 30 astronomical units big if you were opening it up with a little spare to go to the moon. It's a very complex machine. On the top of the machine, you've got the cryogenics. Since this is a superconducting dipole magnet that keeps the beam in place, it needs the appropriate cryogenics. We have about 9 tons of helium in order to cool it down to the temperature that it operates. Our detector is the CMS detectors. We see the snout here. It is 14,000 tons. We built it on the top of on the ground, and then we lowered it down with cranes that we rent from companies that bring out wreckages from the Pacific Ocean. It's one of the most beautiful experiments and most complex experiments that we have built. And it's able, in this particle list that we saw in the table, it's able to capture or reconstruct every single one of them, or infer some of them that you cannot reconstruct because they interact weakly. Which are these? They are the neutrinos. The neutrinos whiz, and they don't leave any traces. You have to infer them by doing energy momentum conservation. These are some pictures from 2010 when we got the first collisions at 2 TeV. This is the head of the Large Hadron Collider, Lynn Evans, and this is the spokesperson then of the CMS that we woke up at 3 a.m. We are showing the first events at higher energy than the Tevatron when we broke the records there. And we are arriving at the Higgs. Peter Higgs visited both experiments very diligently. He knew that once we find the Higgs, we are sending him to Stockholm. So he was good to come to us early on. And what we are going to see here is a time lapse as we accumulate data, what the Higgs looks like. The Higgs look like if something decays, you are going to take the decay products and summon their energy together and infer whether there is a particle, a resonant particle there, and you're going to see something that has a mass that is going to look like above the background, that is going to look like a peak. And what we see here, the blue is what we expect from the standard model, and the dots are the particles as we accumulate them, and then the red is the theoretical model of the Higgs. And the theoretical model of the Higgs, the data appear to track it. This is in the case of 4 leptons. This is the mass of the 4 leptons, which each one of these are the 2 Z particles, bosons, 2 force carriers of the electroweak force. They decay into leptons. You sum all of these energies, you make an invariant mass. This is what you get, the 125 GeV Higgs boson. And this is where we see it. In the case of where we have loop, here we have quantum loops. It's not the Higgs decaying to 2 photons. It's the Higgs through the top going to 2 photons. Very beautiful signature, and Caltech has a tradition of this signature for every calorimeter, even for the SSC that was built with Barry Barish, and then with Harvey Newman, the calibration of the electromagnetic calorimeter so that you measure these photons was done. It's a Caltech product. You see this, in this mode, this is a little blip, so you have to do a lot of data analysis to tease it out. And this is how it looks in the detector. We have billions of protons colliding here, 15 billions of protons. And we get, in this case, let's see what that is. In this case, there are 2 deposits, so it was a case of the 2 photons. You counter masses, you get the Higgs. In this case, it's the 4 leptons. In the one case, it's the 4 electrons. In the other case, it's the 4 muons. You see the 4 tracks that you measure in an LCD-like camera in the tracker. And here you see the 4 tracks from the muon chambers. So you add up these energies, you get a resonance. Promptly also, Peter Higgs sent us the thank you for, I'm going to Stockholm, thank you. And before even Peter Higgs sent us this, the White House sent us a message that this was a crowning achievement. So in the last 5 minutes, I will talk about the puzzles. So the Higgs puzzles are many. First of all, the standard theory together with the Higgs is either fine-tuned, which we call as unnatural, or it needs a protection against quantum corrections. I told you earlier that if I have the Higgs, I need something to protect the Higgs. What is this thing that protects the Higgs? And actually, what is the quantum corrections? It's this type of loops. If you have a heavy particle here, then you get a mass of the Higgs, that it is the Planck mass. This makes no sense. It has to have corrections so that you cancel out, because we know that the mass of the Higgs now is what it is, and it's stable, and we have measured it, and we know it. So we need some protection. Otherwise, we need to redo quantum mechanics from scratch, which we don't think this is the case. So the protections are those superpartners. Those superpartners are particles with twiddles, and they are mirror partners of the normal standard model particles. And the field is a quantum field of the super field of the electron, and you've got a super electron which has spin 0, and an electron which has spin 1/2, and that's what the supersymmetry is doing. A doubling of the spectrum. Remember what happened with Dirac when the theory was being produced? He made a mirror of matter, and he created antimatter in order to tame quantum corrections that were coming about for the mass of the electron. This is the same story here with the last kind of such symmetry. And of course, I wrote a paper together with John Licken. We haven't found them, a crisis in physics. Where are the superparticles? If we had them, they would look like that in the detectors. We haven't found them. We have put limits. This is Javier, who has put the most stringent limits. And part of the Caltech razor Suzy Handers, this razor method we developed here at Caltech together with a colleague from Fermilab and Maurizio, who was then CERN, and then he became Caltech, and then they hired him out again at CERN as a permanent staff. Undergraduate Anne, now she goes to Harvard. Graduate students Javier, Christian, and Alex Mott, who Tesla Motors stole him to do their autopilot. So whoever he didn't like at CMS, he said, don't buy a Tesla because I'm not going to code it to go where you want to go. But the main point is here, if Suzy is the protection we need, we either missed it in the previous runs and it will show up in the 13TeV run. And when I say it will show up, it might show up now because we took 6 months of data already. So it may be there. One of our, and this is what in all the Scientific Americans around the world, in all the different issues, they had the crisis in physics, as was the American issue, except for Spain, where they said, they interpreted the title, the editor wrote in the title, Más cerca de una nueva física, we are closer to a new physics, which is correct. This is the message we wanted to pass. We didn't want to pass no crisis whatsoever. So how would it look? We have an analysis from the round 1 data that has something which we call a tantalizing hint. It would look like if you make a search and you look for a signal, you would get, in many, many cases, you would get observations that match your prediction. And then when some tantalizing hint comes, you get something that it is out of the ordinary. We have such a tantalizing hint, but it's not enough to exclaim Eureka. And when we are looking now beyond the Higgs, we have to be careful when we will say that there is a tantalizing hint. We have more than this. We have more tantalizing hints than this, and you will hear it in the news. Another part of the puzzle is that with the Higgs mass that we found, I call this a tripolar disorder of the Higgs, because it's okay, we found the Higgs how we expected it. A lot of people call it the simple model, very beautiful, everything okay. But then if you try to do the calculation of the electroweak vacuum with the Higgs mass we measured and the top mass we measured, that was the vacuum, the electroweak vacuum, that it can tell you how the universe will move, whether the universe is in a false vacuum and will tunnel out in a different, more stable vacuum. And we find that it is in between stable and unstable, it says that the universe will bubble out in a more stable vacuum, so this will be destroyed and another one will appear. That doesn't sound good. If you put new physics in there, this problem will be solved. This is another indication that new physics has to be there. As for SOSY or other models, it's also problematic, this number. It sits on the border where if you have SOSY, it's not the canonical SOSY. You need to invent something more, different kinds of models. If it's other models, composite Higgs, etc., again, it sits on the edge of the validity of those models. That was a paper actually by Politzer and Wolfram here at Caltech that they wrote back then that you can have a false vacuum where you tunnel out of the vacuum in a different, better vacuum. And we hope that this is not the case for the electroweak vacuum at all. One more thing about the symmetry breaking and complexity. I showed you previously the vacuum bubbling out. And that doesn't look like a simple system. It's a really complex system. In fact, the quantum vacuum is a many-body system. So the ideas that led to the Higgs mechanism, electroweak symmetry breaking, are in fact ideas that come from the study of the solids. And we said that actually field theory is the language also of solids, of condensed matter and particles. And these type of ideas generated, and experimentally also, as we will see, generated the idea of the Higgs mechanism by one of them, Phil Anderson, who wrote a paper that was called More is Different, and argued that spontaneous symmetry breaking is in fact a property of large systems. Now, we don't have only the Higgs, the cosmic kind of Higgs that we're talking about, but we have light Higgses in different other quantum systems. And very recently, we hired somebody at PMA that has a Higgs, which is 200 hertz, a very tiny Higgs. It's in this kind of scale, very low energy, in superfluid, in two-dimensional superfluid Mott type of superfluids. So in condensed matter, you have more types of symmetry breaking that produce states that look like the Higgs. So beyond the Higgs now, is it the questions that we are trying to answer? Is it the standard model? Does it behave as predicted? Is there more than one looking like Higgs? How many more? And this defines the program that we are doing right now, a very exciting program, because we expect that we will find something, maybe not supersymmetry. Incidentally, supersymmetry predicts 5 kinds of Higgs bosons, that they differ in mass and their other quantum properties. And I'm going to close now in 2 or 3 minutes. I will circle back to dark matter. And we saw dark matter in the large-scale structure, and we saw how matter hinges on top of dark matter. And by the way, also dark matter, the first time that dark matter was postulated was at Caltech by Zwicky, and I didn't put his picture here. I should have. But now, in terms of the dynamics of galaxies, he predicted it in clusters of galaxies, so sets of galaxies, or nebulae as they were called. So in galaxy, we said we have stars, we have gas, we have dust, we have a black hole in the middle, and then we have dark matter. We have dark matter because when we look at the rotation curves, you would expect that as you go out, you would get slower and slower, the stars moving around in the galaxy, in the spirals here in the galaxy, but they don't. You observe in the curves that they go and they flatten out, and instead of having Newtonian 1/r kind of behavior in the rotation of the stars, you don't get that. The same thing if it is clusters of galaxies, the galaxies that go around each other. So this is very, very peculiar, and this is telling you that there is extra gravity there. Where do we get the extra gravity? We hypothesize that there is something which we call dark matter because we don't know what it is. It is there. The gravity is there, but we don't know what it is. We call it dark matter, and we put it initially as a halo, dark matter halo. We see it with lensing because dark matter, you're not going to be seeing anything, but you will see if you have matter, you will see something like as if you have a lens. This is why we call it the lensing, and this is the kind of lensing patterns that you see if you have a chunk of dark matter in the middle behind a galaxy. You will see these lines because the galaxy will be projected, the light from the galaxy will be projected around in many places. It will be something like the optical lens. I remind you, this is the large-scale structure, and then these are models of which kind of dark matter density we should have in order to see this type of patterns. Theorists, of course, they go out of their way and they created a plethora of dark matter models. There are so many dark matter models today, and all of them are hinging on the fact that the dark matter is a particle. And as such, we have now all these models to exclude or discover, which is a good thing. Yesterday, there was an article of Symmetry magazine that describes a huge set of this type of dark matter theories. And here's again the universe energy density composition. To connect it with the Higgs, the dark matter, we know that it interacts with gravity. We have seen it from the cosmology observations. For particle physicists, you want to know if it interacts with matter other than with gravity, what else could it interact with? It would interact with very, very super weak forces. Which are the super weakest forces that we have? The electroweak forces, like the force that is mediated by the Z boson, or the one that is mediated by the Higgs boson. So the Higgs could be indeed a portal to dark matter. Of course, it's possible that there is some exotic dark force also. And this is the job of the theorists again. For us, we are looking for these with monojets and with other final states. We're looking for dark matter in all of that. Closing now, and I'm sorry I'm taking a little longer. The Higgs connections to the beyond. Is there a Higgs portal to dark matter? How does the Higgs talk to neutrinos? Are there dynamical origin of fermion masses, mixings, and this matter-antimatter asymmetry? And the extra credit that we talked a little bit in the beginning, is the Higgs related to this inflation or what we call dark energy? And this is a long, very big program that demands experiments like the LHC, of course, but also probes in space and other experiments that are lower energy. So we don't have an evidence for supersymmetry so far at the LHC. Without supersymmetry or something like that, we don't understand how the Higgs boson can exist without violating the basic mechanisms of quantum physics. And the apparent instability of the vacuum, if you want to consider that it's standard model only, is a mystery. So either we are going to discover something very soon, maybe not the superpartners that we envision, or we are going to have radical new ideas. The final point that I'm going back again into space-time is what I call space-time hacking and gravity. Space-time, this nice notion that we had about the geometrical space-time, it seems to be progressing in how we think today. And this is what we call, theoreticians are doing this tension network of entangled particles, and they think this is in fact behind space-time. So there is a paper from 2 days ago in Nature, or 3 days ago in Nature. No, actually, it's November 16. The quantum source of space-time. It's a very nice account of how we are progressing in the way we think of space-time, and it's going to be in a graph here. We're thinking of space-time. We're going to see space-time, the geometry, where it deforms, where you have mass, where you have large masses. So this is the galaxy. And then we think of space-time. If we go into the quantum realm, we start thinking of space-time having to do with something with the quantum world. And what will that be? That becomes very complex. There is complexity, and that could hinge on the fact of entangled pairs, which was the network that we had sketched here. So could it be? Many people think that and in my lectures when I was explaining extra dimensions, in every lecture I was finishing with the fact that Some of the most famous physicists in the world were saying that space and time are doomed, they don't exist, they are an illusion. And of course, this kind of, when this kind of quotes are coming about, you have to wonder what is really space and time. And I want to say that at Caltech, there is colleagues of us that are dealing with this type of problems, theorists, Alexei Kitaev and John Preskill. And I call this a new frontier because who knows where this is going to take us in terms of our understanding of the universe. Sorry, I am late. Thank you.